Hello students, welcome to my class on operating system. I am Shravani Kundu, Assistant Professor, Department of Computer Science and Engineering, Guru Nanak Institute of Technology. Today I will discuss the topic process scheduling. So this is the overall objective of this lecture. After completion of this lecture, the students will be able to understand what are the needs of scheduler and what are the different types of scheduler and for which case the which scheduler should be used. So before this going to the details, first I will introduce what is the process scheduler. If you can remember that while we are discussing about the different services of the operating system, so there was one of the most important service, that was the scheduling service. So scheduling is a part of the operating system. This is a functionality provided by the operating system. So in the operating system provides the service called scheduler, and the scheduler selects the process from the different queue and assign it to the CPU for the execution. So you can see over here that there are different types of schedulers. Scheduling queues are there with which the scheduler is associated. The scheduling queues are job queue, ready queue, and device queue. So you go to the next slide. In this slide, you can see that this is the process state diagram, which I already discussed in my previous lecture. So here, as I discussed, that with each state, the scheduling queue is associated. Fine. So here, the scheduling queue, which is associated with the new state, is called the job scheduler. So with the new state, a scheduling queue is associated with this new state. So a queue is there. So this queue is called the job queue. Okay. Now, the scheduling queue associated with the ready state, that means the queue which is associated with the ready state, this queue is called the ready queue. So I already discussed those things. And the queue associated with the waiting state is called the waiting queue. Okay. So while the process should be selected from each of the queue, the scheduler takes a very important role, because the task of the scheduler is to select the process from the queue and assign it to the next state. For example, when a process is ready for the execution and it is present in the job queue, so job queue has multiple processes which are ready for the execution. Now the task of the scheduler is to select the process from this job queue and assign it to the ready state for the execution. So when the process will come to the ready state, it will be inserted in the ready queue. So many processes are already present in the ready queue, and the processes which is present in the ready queue are waiting to get the CPU. Now a scheduler is also associated with this ready queue. That scheduler select a process from this ready queue and assign it to the CPU for the execution. Similarly, in the waiting state, a queue is associated which is called the waiting queue, and all the processes present over here, either they are waiting as they are performing the IO operation, or they are waiting to get the IO devices. So if they are waiting to get the IO devices, then again the scheduler will work over here. So consider there are two processes like P1, P2. So if both the processes are waiting for IO devices, then the scheduler works on the scheduling this waiting queue, will select either P1 and or P2 depending on some conditions. So that is called the scheduling criteria. So based on the scheduling criteria, any process will be selected, and for that process the IO devices will be assigned so that the process can complete the IO operation. And after completion of the IO operation, it will go back to the ready queue and will be inserted in the ready queue. Fine. So here you can see the scheduler takes a very important role for the process execution and switching from one state to another state. And the scheduler is associated with each queue. But no scheduler is present in the running state and the terminate state, because in the running state only one process is there which is executed by the CPU. So there is no concept, no requirement of the scheduling. So no scheduler is present. That means in the running state there is no queue. No queue is there in the running state. And as there is no queue, then no scheduler is also present in this state. So scheduler is basically associated with the queue, where from where we have to select the process for the different operation. Fine. So you can see in my next slide that what are the how the process change from one state to the another state. So as you can see over here that in the process entered in the ready queue. Fine. So the process entered in the ready queue. So this is the entry point. So this point we can say this is the entry point. Fine. So the process entered at this particular state. Now after entering through this ready queue, the scheduler will work over here. So scheduler is present over here. Now scheduler select the process from the ready queue and it sent the process to the CPU for the execution. Now CPU analyze the code. If the instruction should be executed by the ALU or control unit, then the CPU will execute that instruction. And if the instruction is associated for some IO operation, for example, if the instruction is like printf or if the instruction is scanf. So in this case, the scheduler, the CPU send those processes in the waiting state to perform the IO operation. Fine. So from the CPU, a process can jump to the waiting state to perform the IO operation. And another way, if a process complete its time slice, that means as I discussed that there is a time sharing operating system. So this operating system is called the time sharing operating system. So this time sharing operating system basically works on the time slice. So that is called the time slice. Time slice is nothing but a time quantum. So that quantum basically decides that a process can execute the CPU. A process can be executed by the CPU for how long time. So let us say the time quantum t is equals to 2 nanoseconds. So that indicates a process can execute by the help of the CPU for 2 nanoseconds. That means a process can reside inside the CPU for 2 nanoseconds. And within the 2 nanoseconds, if the process is not able to complete its job, in that case, the process has to leave the CPU. So this time slice expert explained in case of time sharing operating system, if that time slice, that means if for this example, if 2 nanosecond gets over, so in that case, the process will change its state from the running state to waiting state. So as you can see in the previous diagram, so there is my ready, so this is called my ready state and this is my running state. Fine. So running state means the state associated with the CPU where the process is executed by the CPU. So if the time slice expired, so in that case the process will jump from the running state to ready state. Clear? So here you can say that if the time slice expired, then the process will shift from running state to ready state. And when the process will shift from running state to ready state, then after changing its state to the ready state where the process will reside, the process will be inserted in the ready queue. So this is the ready queue. Okay. So the process, once the process will change its state from running state to ready state, it will be inserted in the ready queue. So as it is inserted in the ready queue, that means the CPU is free now. So as the CPU is free, that means we need to perform the scheduling operation. So this diagram basically explain when the system need to perform the scheduling operation. So in the first case, you can see that if there is some IO request, definitely the process has to switch from running state to waiting state. So this is waiting state. So process has to switch from running state to waiting state. So as the process will switch from running state to waiting state due to performing the IO request, the CPU is now free. And you remember one thing, this is very important, the scheduling operation will take place only that time when the CPU is free. So as the process shifts from running state to waiting state, the CPU becomes free. And when as the CPU becomes free, the scheduling needs to perform, and scheduling operation will be performed where? The scheduling operation will be performed in the ready queue. So the process which is present in the ready queue are the process which are waiting to get execute. Among them, one process will be selected and that process will be assigned to the running state. So you can see that while some IO operation needs to be performed or IO request is generated, then the scheduling operation takes place. Again, you can also understand that if the time slice expired, then the process will change from running state to ready state. Again, the CPU becomes free. Then again, we need to perform, the system need to perform the scheduling operation. And there is another two cases that when the process will complete its generate some child process. Fine. So suppose there is a parent process. So this is a parent process. Now this parent process invoke or create a child process. So when a parent process needs the child, creates a child process, and the child process needs to be executed before the parent process, in that case the parent process has to stop its execution and it has to go to the ready state, or it has to wait. So when a process has to wait, it will go from running state to waiting state for the waiting purpose. So you can see that due to the creation of the child process, that means the fork system call which is used to create the child process, due to the creation of the child process, the parent process stops its execution, CPU becomes free, and we need to perform the scheduling. Again, there is another instance that if some interrupt occur, that means as I told you that it may happen that in the ready process is in running state, that means a process is executed by the CPU, and in that time another process enters to the ready queue and which has the higher priority than the process which is running in the running state. Fine. So suppose here for example P1 is in the running state and P2 is entered in the ready queue, and the priority of the process P2 is higher than the process P1. So in that case, what happens? The P2 has to forcefully send back to the ready state. So as the process P1 will be sent back to the ready state as this priority is lower than P2, so the CPU becomes free. So in that time, we need to perform the scheduling. So that means while the interrupt will occurs, at that time also we need to perform the scheduling. So this overall diagram explains the different scenario, different instance when the scheduling operation needs to be performed. So as you can see that if there is some IO request, the process needs to perform the scheduling operation. If the time slice expired, the process needs to perform the scheduling operation. If the parent creates a child process, that means due to the execution of the fork system call, the process needs to perform the scheduling operation. That means the system needs to perform the scheduling operation. And while there is interrupt, in that time also the system needs to perform the scheduling operation. Fine. So this is the different scenario while we need the perform or when we need to perform the scheduling operation. Okay. So you can see that the scheduling operation needs to be performed in different places. Either we need to perform the scheduling operation in the job queue, or we need to perform the scheduling operation in the ready queue, or we need to perform the scheduling operation in the waiting queue. So there are different queues and where we need to perform the scheduling operation. Now, who performs the scheduling operation? So there is a service which is called the scheduler. So that service provides the scheduling operation. So you can say that scheduler is the service which is provided by the operating system, and that service helps us to schedule or select the process from different queue. Scheduling is nothing but the selection of process from different queue. Fine. So there are many types of schedulers are there. So those schedulers are called the short-term scheduler, long-term scheduler, and mid-term scheduler. So basically, there are three types of scheduler we can explain. So those schedulers are short-term, mid-term, and long-term. Fine. So we are writing it over here, those different types of schedulers. So they are short-term, then long-term, and the last one is the mid-term scheduler. Fine. Now it is very important to note that which scheduler will work in which queue. Fine. This short-term scheduler works on the ready queue. Okay. The short-term scheduler works on the ready queue. The long-term scheduler works on the job queue. And we will discuss this mid-term scheduler later. So first we will discuss the short-term scheduler and long-term scheduler. So as you know that it works on the short-term scheduler works on the ready queue, definitely this scheduler select a process from the ready queue and assign it to the CPU for the execution. Fine. So this short-term scheduler is sometimes known as the CPU scheduler because it is scheduling the process to the CPU. Fine. Now the next one is the long-term scheduler. Fine. Now long-term scheduler basically works on the job queue. So if you can remember the process state diagram, so in our process state diagram there is a state called new. So with the state new, a queue is associated. That queue is called the job queue. Fine. So this is called the job queue. And there is another state is ready state. So you can remember that the process is shifted from the new queue, new state to the ready state. So who will select the process of in the new state, the job queue is associated. So all the process which is ready for the execution, they are new to the system. So they will be inserted. So let us say that process P1, P2, P3, they are present in the job queue for the, because they are new and they want to start their execution. And they can start their execution. They can get their CPU only. They will be present in the ready queue. Until and unless they will get the place in the ready queue, they cannot start their execution. Fine. So the long-term scheduler select a process from this job queue. Fine. So the long-term scheduler select the process from this job queue, from this particular queue, and it assign that process to the ready state. So you can see that this scheduler, long-term scheduler, as it is associated for the selection of the job, so this long-term scheduler is also called the job scheduler. So here you can see the term job scheduler. So the long-term scheduler is also called the job scheduler. Fine. And the short-term scheduler is called the CPU scheduler. Fine. So these two scheduler is very important. You have to remember that short-term scheduler works on the ready queue. Long-term scheduler works on the job queue. Job queue means the long-term scheduler works on the new state. The short-term scheduler works on the ready state. And the task of the long-term scheduler is to select a process from the new state and assign it to the ready state. And the task of the short-term scheduler is to select a process from the ready state and assign it to the CPU for the execution. Fine. Now, before discussing the mid-term scheduler, you have to remember, you have to understand one important term that is called the degree of multiprogramming. Okay. Now, what is the degree of multiprogramming. So you can see that in the CPU is basically used to perform the execution of different process. CPU cannot perform any sort of IO operation. Fine. So if I need to perform the IO operation, you have to take the help of the IO devices. So you can say that what is the degree of multiprogramming? The degree of multiprogramming says that how many programs can be executed by the system, by the CPU at the same time. What is that? That means, suppose this is your CPU, right? Now, your CPU executes the process P1. So in that case, the CPU is busy to can execute only a single process at this moment, and in our operating system there is no other process to execute. So in that case, the degree of multiprogramming is 1. So here the degree of multiprogramming is equals to 1, as there is only one process which is executed by the CPU, and in the system there is only a single process. No other process is there. So degree of multiprogramming says that in our system, how many process can be executed simultaneously. So if the processor CPU can execute one process at a time, then the degree of multiprogramming is 1. That means at least this is a single processing system. Now, if our processor can execute more than one process, in that case, the degree of multiprogramming will be more than 1. So let us say if the CPU execute the process P1 and P2 simultaneously based on the time sharing basis or some other, using some other concept, how they are executing, we will discuss them later. But assume the two processes are executed by the CPU simultaneously. So in that case, the degree of multiprogramming is 2. That means your system, your operating system can execute two processes at the same time. Fine. Now, here there is a very important concept which is called the midterm scheduler. Now, another thing is that among those processes which are executed by your system, the process can be of two different types. The first type of process is called the IO bound process, and the second type of process is called the CPU bound process. Fine. So the processes which are executed by the system, those processes can be differentiated and be categorized in two ways. All the processes which are executed by the operating system, the entire set of process. All processes can be designated, can be divided into two categories. One is the IO bound process and second one is the CPU bound process. Now, which process is called the IO bound process? So if a process has multiple IO operation and minimum number of executable statement, then that process is called the IO bound process. So what I am saying, that if a process has multiple suppose you are writing a program, so like that you are writing the statement like that, function if. So inside this function if, your statement is like that: for I equals to 0, I less than 10, I plus plus. And what you are doing under this for loop, you are printing the statement. You are printing the statement printf hello. You are printing this statement. Okay. Under the for loop. So this is our function if. This is the task of the function if. So what the process will do? For each iteration, it will print hello. And where it will print the hello? It will print the hello to our display device. Okay, so it will print it to the display device. So as it is printing to the display device, that means which operation need to perform? It needs to perform the IO operation, output operation. That means the process needs the IO device driver or IO services of the operating system to complete its job. It doesn't need the control unit or arithmetic logic unit. So as you know that the CPU has two different parts. One is the ALU, arithmetic logic unit, another is control unit. The arithmetic logic unit is used to perform the arithmetic operation, and control unit is used to control the operation, all sorts of logical comparison. So here a control unit performs the decision and helps the ALU to work perfectly. So what you can say that here you can see for this particular program there is no need of CPU. All the tasks, that means this printing stuff needs to be performed by IO devices. So this type of job is called the IO bound process. That means where most of the instructions are IO related, and that means the process spends its maximum time in the waiting queue. So if the process spends maximum time to perform this IO operation, then the process is called the IO bound process, and for those process the CPU burst time is very short or small. CPU burst time very small means it takes a minimum amount of time, and during that time it's spent with the CPU. That means the time it takes the CPU is very less. Fine. So that process, this type of process is called the IO bound process, where the process needs to spend most of its time to perform the IO operation. Fine. Now consider there is another type of process. The same we will write the same function over here. So here you can see the another type of process where the process needs to perform the most of the operation, and most operations are computational operations. So consider the same function f, and here we write the instruction like for I equals to 0, I less than 10, I plus plus, and here I will write the statement. So that C equals to, so we know you have initialized the C before that. So C equals to 0 we have initialized. So we can write C equals to C plus I. Fine. So what we are doing over here? So you can see that for this particular code, there is no IO operation. So for each operation, for each iteration, I need to, so there are total overall 10 iterations, and in each iterations I need to perform the addition operation C plus I. So this addition operation I need to perform, and to perform this addition operation we need to take the help of the CPU. Fine. So this type of process where the process spends its maximum time to perform any sort of computation, and it spends a very few time to perform the IO operation, then that process is called the CPU bound process. Clear? So there are two types of process. One is the IO bound process, and second type of process is called the CPU bound process. Fine. IO bound process spends its maximum time in the IO device and less time in the CPU, and the CPU bound process spends its maximum time in the CPU and less time in the IO device. So now the thing is that if we have the in our CPU, in our system, if most of the process are IO bound process and most of the processes are CPU bound process, in that case what will happen? If most of the processes are IO bound process, in that case all the process will wait in the waiting state, and if most of the processes are CPU bound process, then all the processes are busy to perform the operation with the help of the CPU. Fine. So you can see that what happened over here. So in that case, if most of the operations, most of the processes are IO bound, so if most of the processes are IO bound, so in that case they will spend maximum time in the waiting state. Okay. So in that case, CPU is idle. So consider your operating is the multi-programming operating system, and in the ready queue multiple processes are there. In the ready queue multiple processes are there for the execution. And consider in my ready queue, this is my ready queue. There are processes like P1, P2, P3. Three processes are there, and all processes are IO bound process. So what happened in that case? The process will go to the waiting state. First, the process P1 will be assigned to the running state. It will be assigned to the running state. And after going to the running state, the CPU identify no, it needs to perform the IO operation. So it will go to the waiting state and it will try to perform the IO operation. Next, P2 will be assigned to the CPU. And while the P2 will be assigned to the CPU, again CPU can identify, yes, it is a IO bound process, IO operation needs to be performed. So P2 will be sent to the waiting state. So in the waiting queue, the P1 will comes over here and it will wait for the IO operation. P2 will also comes over here and it will wait for the IO operation. And while the P3 will be assigned to the CPUs, again instantly P3 will be sent back to the waiting state to perform the IO operation. And here you can see that there is no process. So entire ready queue is my empty because all processes are sent to the waiting state and they are waiting there to perform their IO operation. So here there is no more process in the ready queue and the CPU is idle. CPU is not performing any operation, it is just idle. So as the CPU is idle, then the operating system identifies that the degree of multiprogramming decreases. So what happened over here, and all the processes are waiting inside the waiting queue. So overall the degree of multiprogramming will decrease. That means the process will take more time for the execution. The process will take more time for the execution. So what happened over here? So if in that case, this is not a correct mixture of the process. Again, consider another scenario that if in the system all the processes are CPU bound process. So in that case, what happened? The IO devices will not perform any job. It will just sit idle. So consider another situation where the ready queue has a set of processes like P1, like P2 and P3, and all three processes are CPU bound. That means all the instruction, that is most of the instruction of those processes are CPU related, computation related. So they will spend maximum time in the running state. So while P1 will be executed by the CPU, then P2 and P3 will waiting state. Now P1 will take long time for the execution because all of its instructions are CPU bound, and P2, P3 will wait in the ready queue. But in the waiting state, that means in the IO devices are not doing any operation, they are sitting idle. So again, the utilization of the system resources are not good for the IO bound, CPU bound process. So what the task of the midterm scheduler? The task of the midterm scheduler is that it should create a good mixtures of the IO bound process and CPU bound process inside the ready queue. So what you can see over there, so in the ready queue has our set of processes, fine, P1, P2, P3, P4 like that. Now the midterm scheduler checks among all the processes which are present in the ready queue, or what is the type of the process. So it observes the system. If a process or most of the processes are CPU bound, then what happens? It will send some process to the backing store. Backing store means secondary device. So it will send some processes to the secondary device and try to bring most IO oriented process in the, try to insert most IO oriented process, IO bound process in the ready queue. So what happened over here? So the task of the midterm scheduler is that it should create a good mixture of the CPU bound process and IO bound process inside the ready queue, so that the CPU and IO, both the devices, should be utilized utilized in certain percentage. That means no one should be sitting idle. So if all the processes are CPU bound, IO will wait, it is remain idle. If all processes are IO bound, then the CPU will sit and it will remain idle. It will not perform any work. So the task of the midterm scheduler is to create a good mixture of the CPU bound process and IO bound process, so that the overall utilization of the CPU and IO is good. And if it happened that in the ready queue, most of the process are CPU bound process, in that case, it will send back all the some processes to the backing store or secondary device, and it will bring some IO process from the secondary device, IO bound process from the secondary device to the ready queue, to create the good mixer. And the same thing is true for the IO bound process also. If in the ready queue, most of the processes are IO bound, so the processes will be sent to the backing store. So IO bound process will be sent to the backing store, they will be sent to the backing store, and the CPU bound process will bring from the secondary device to the ready queue to create the good mixture. So the midterm scheduler basically helps the system to utilize all the resources is very well, and it also increase the degree of multiprogramming. So degree of multiprogramming means that how in per unit of time the system can produce how many outputs. So based on that we can decide the degree of multiprogramming. That means how many processes can be executed by the system at the same time. So if they suppose if there are good mixture of IO bound process and CPU bound process, so at a single instant of time, two processes are executed by the system. One is executed by the CPU and another is executed by the IO devices. So you can see the degree of multiprogramming will increase. But if all the processes are IO bound or CPU bound, then all the processes will remain idle, only one process will be executed by the system, and that in that case the degree of multiprogramming will decrease. Fine. And another important thing is that you can observe over there that if the processes are not the good mixture, that means all are IO bound or CPU bound, then the midterm scheduler will send all the processes to the secondary device. So it is taking the processes from the ready queue, that means from primary memory, and storing it in the secondary memory. Fine. So what it is doing over here? So the midterm scheduler, so this is, we can say this is our main memory and this is our secondary memory. Fine. So if there is a not good mixture of the IO bound or CPU bound process, that means all processes either IO bound or CPU bound, then the midterm scheduler sent the process P1 or set of processes Pi rather from the main memory to the backing store, and it will bring some another types of process from the secondary devices. Let us say this is PJ, from the secondary devices to the main memory. So this sending back the process from the main memory to the secondary memory and bringing the process from the secondary memory to the primary memory, this overall phenomenon or incident is called this process is called the swapping. So what is swapping? Swapping is a process by which the process will be sent back from the primary memory to the secondary memory, and some processes from the secondary memory will bring back to the primary memory for the execution. Fine. So this is all about the midterm scheduler. So in summary, there are 3 times scheduling is very important terms, very important criteria, functions of the operating system. Scheduling takes place when the CPU is free. Scheduling of this scheduling operation works on the queues. 3 queues are there: job queue, ready queue, and waiting queue. So scheduling operation will be performed on 3 queues, and the service that performs the scheduling operation, that service is called the scheduler. Schedulers are of 3 types: short-term scheduler, mid-term scheduler, long-term scheduler. Short-term scheduler works on the ready queue, long-term scheduler works on the job queue, and mid-term scheduler basically creates a good mixture of the CPU bound process and IO bound process, so that the overall degree of multiprogramming can be increased for that system. And to increase the degree of multiprogramming, Some processes need to be sent to the secondary memory and some processes need to bring back from the secondary memory to the primary memory, and this process is called this situation, this phenomenon is called this technique is called the swapping. Clear? So that is all about the process scheduling.